Hi class, today we're going to talk about the fundamentals of engineering transportation portion of the exam. There's 5 sections on this exam: geometric design, pavement system design, traffic capacity and flow theory, traffic control devices, and transportation planning. Section B, which is pavement system design, will not be covered in this class. Please talk to Dr. Abbas about the future in this subject. Geometric design is the first thing that we're going to cover today. We're going to start with vertical curves. Vertical curves are parabolas. Vertical curves are referenced in the horizontal plane, so length is horizontal distance, not along the line. And the primary use is equal tangents in design. The vertical curve geometry equals y equals ax squared plus bx plus c. When you rearrange that, you can see that y equals c plus bx plus ax squared, where y is the elevation, c is the PVC or the point of vertical curve, bx is g1x, and ax squared equals a over 200L ax squared. Make sure you stay consistent with stationing and grades. Make sure you pay attention to, in feet, it's 0.05 is the percent multiplied by 100, or stations is 5 times 1. Other formulas of interest is L equals K times A, which is the length of your curve. A is the geometric difference, G1 minus G2 absolute value, and the turning point XTP equals L G1 over G1 minus G2. Keys to solving vertical curves. They're the exact same for both crest and sag curves. Step 1, go ahead and draw it. Step 2, find the VPI. Step 3, find the length of the curve. There's 2 ways to find it, the L method and the K method, which both involve the SSD method. Step 4, find the PVC. Step 5, find X. There's 2 ways to find X, the turning point and the point on the curve. Step 6, find the elevation of X. At this point, I would recommend that you go through these 6 steps again when you're studying for the exam. Example 1, 2 grades, plus 125 and minus 275 intersect at a station 18 plus 00 at an elevation of 886.10 feet. If the length of the vertical curve is 600 feet, what are the elevations and stations of the VPC, VPT, and TP? Givens there at the top, the VPI, draw it. Elevation at PVC equals 886.10 minus 1 half L times G1. Solve for it, 882.35. Location of the PVC, 18 plus 00 minus 3. That's half of your length of your vertical curve equals 15 plus 00. Find elevation at VPT equals your PVC plus G1x plus G2 minus G1 over 2L x squared. That answer is 877.85 feet. And the location of your VPT is 15 plus 00 plus 6.00. At this point, I'd suggest that you review this problem again. An alternative solution. The difference here is this one is used in feet and in decimal points for the grade. Again, you will see that the elevation of the PVC is still 882.35, and the elevation of the VPT is 877.85. Turning point. This is the high point and low point of the curve. X turning point equals L G1 over G1 minus G2, which equals 1.8 stations from the beginning of the curve. PVC, BVC, EVC. The elevation of the turning point uses the exact same elevation of the other equations. Here you'll see that the elevation turning point is 883.52 feet, and the station of the turning point equals PVC plus X, which is equal to 16 plus 88. I would take a minute and review this one as well. Find the length. Sometimes they will ask you to find the length of the curve. Step 3, find the length of the curve. There's 2 ways to find L. K method, SSD method. A crest curve is to be designed to join a 2% grade with a minus 1.25% grade at a station of a 2-lane highway. The design speed of the highway is 55 miles an hour. The VPI is at 15 plus 00 with an elevation of 500 feet. What is the station height of the turning point and what is the elevation? As you can see here, the first thing that we did is we found L. L equals K times A. You'll have to go to the tables provided for you to solve for K. And you'll see A is the geometric difference between the two, 370.5 feet. Find the PVC elevation, 496.3 feet. Find the location of the PVC, 13 plus 15. Turning point, you can see there is 2.12 stations past the beginning. And find X along the curve. This is just a random point that can be taken on the curve. As you can see there, we're looking at station 16 plus 0, 0. And X is equal to 1. Horizontal curves, geometrics. Horizontal curves are primary, simple curves and have a constant radius. Horizontal curves are referenced along the curve, so the length is measured along the curve. Tangents are equal, so curves are symmetric. Step 1, find the PI. Step 2, find D or R. Remember, the two go hand in hand. Step 3, find the PVC. Usually you need to find the tangent length first. Step 4, find the length of the curve. Step 5, find the length of the curve. Step 6, find the remaining components. Could be M, E, for example. Compute T, L, E, M, R, and stations PC and PT for the circular curve described below. Highway curve with a degree of curvature of 3 degrees, 30 minutes. I, 24 degrees, 45 minutes. PI station 30 plus 0, 0. Givens. Find R. 5729.58 divided by D gets converted to 3.5. Knowing D and R is very important. Find the PC, beginning of the curve, equals your PI minus your T. T is always R tan I over 2, which is equal to 3.59 stations. I would encourage you to use stations over feet. PC equals 30 plus 0, 0 minus 3.592, which equals 26 plus 41 stations. Find PT. PT equals PC plus L. L equals 100 I over D, which equals 707.1 feet. PT equals 26 plus 41 plus 7.07, which equals 33.48 feet. This problem should take you about 3 to 4 minutes to do on an exam. E equals R tan I over 2, tan I over 4, which equals 38.94 feet. M equals R, 1 minus cosine I over 2, which equals 38.03 feet. And the length of the chord equals 2R sine I over 2, which equals 701.7 feet. Keys to solving horizontal site offsets. Step 1, find R, usually to the center line of the highway, unless otherwise defined. Step 2, find little r. Little r is the middle of the inside lane. Remember, the two go hand in hand. Step 3, find the stopping sight distance. Step 4, solve for M, sometimes called HSO. Remember that M is referenced to the middle of the inside lane. Watch out if they have M referenced to the edge of the pavement. Givens. Example 5. 4 lanes, 12-foot lanes. Degree of curve is 4 degrees. Design speed 45 miles an hour. First, calculate big R as drawn here. Same as before. 5729.58 divided by D equals 1432.4 feet. Little r equals big R minus delta, which equals 1432.4 minus 18, which is 1 lane and a half. 1414.4 feet. M, or HSO, equals R, parentheses, 1 minus cosine 28.65 stopping sight distance divided by R. M, or HSO, depending on how it is 11.6 feet to the middle of the inside lane. M, or HSO, to the edge of the pavement is 5.4 feet. So make sure that you're careful that you watch for that extra spot. This problem should take you about 2 to 3 minutes. They're going to ask you for M, or R, or HSO. Remember, you're looking for little r in the equation, not big R. Super elevation, basic formulas. R min equals V squared over 15 E plus Fs. A horizontal curve with a radius of 2,100 feet is to be constructed on a high-speed road with a design speed of 60 miles per hour. Determine if the roadway requires super elevation. If so, how much? What would the degree of curvature be if we increase the super elevation to 8%? Given, radius equals 2,100 feet. Remember, they could hide radius with D as well. Design speed, 65 miles an hour. Notice in this that velocity is based on miles per hour, and your E in this case is 2.4%. Second one there, let's assume that we increase it, the super elevation, to 8%. What's the radius? Rmin equals V squared over 15E plus Fs. So our Rmin now is 1482.5 feet. And in the bottom one, you can see that we're solving for D. Make sure that you know that it's 3.86 degrees, which is equal to 3 degrees, 51 minutes, 36 seconds. Make sure on an exam that you know how to use the degrees, minutes, and second function on your calculator. This problem too should take a couple minutes. I would encourage you to stop and review this as well. Speed, flow, density relationships. The top left is flow versus density. The bottom left is speed versus density. The bottom right is speed versus flow. Make sure that you have these general parameters memorized when you go into the exam. Example 7. Dr. Schneider is driving on I-77 at 70 miles per hour, counts 15 vehicles, including his own, and 3 lanes between his car and the next milepost at 0.2 miles away. Determine the density of the roadway. Find the approximate flow rate, Q, for the roadway, and find the maximum flow rate, Q max, for the roadway. Givens up top. 1. Density, vehicles per mile per lane. 15 vehicles, 0.2 miles, 3 lanes, equals 25 vehicles per mile per lane. Approximate flow rate, Q, equals density times space mean speed. Density, 25 vehicles per mile per lane. Speed is 70 miles per hour. Gives an approximate flow rate of 1750 vehicles per hour per lane. Max flow rate, Q max, equals jam density times space mean speed. Jam density, 5,280 feet per mile. 20 is the standard length for a car. 5 is the standard distance between two cars. So this is equal to 211.2 vehicles per mile per lane. SF equals S divided by 1 minus D over jam density, which equals 79 miles per hour. That's the flow rate, that's the speed. Q max, SF over 2 multiplied by the jam density divided by 2 equals 4,171.2 vehicles per hour per lane. Derivation of a Poisson equation. Probability equals lambda t to the x, e to the minus lambda t over x factorial. This is dealing with gap acceptance. Next step, what do we do from now? Go back to the definition of gap acceptance, which means the probability of x being 0. For a vehicle to move, the time t must be greater or equal to a critical gap. For this to happen, x has to be equal to 0. Example 8. 360 vehicles are counted at a specific highway location in 1 hour. Assume the arrival of the vehicles is Poisson distributed. Estimate the probabilities of having exactly 0, 1, 2, 3, 4, and 5 or more vehicles arriving over a 20-second interval. What are the total number of intervals per group? And what is the probability that at least 3 vehicles will arrive in 20-second time interval? Givens, 360 vehicles, t equals 20 seconds. Make sure that you convert to your lambda into the same units. In this case here, that's 0.1 vehicles per second equals lambda. You can see the numbers there for number of cars from 0 to 5. P sub n equals lambda t n, e to the minus lambda t over n factorial. So for 0, that's equal to 0.135. And then frequency equals probability multiplied by the number of intervals, which is equal to 24. And in this case here, what's the probability of n being greater than 3? It's equal to 1 minus 0.676, which is equal to 0.32. This style of problem should take you, again, just a few minutes to do. Next, we're going to talk about Q diagrams. This is an example of a lane closure. An incident or construction causes a single lane closure on a 2-lane freeway, reducing capacity by 1/2 to 1,800 vehicles per hour. The y-axis is the cumulative vehicles. The x-axis is the time. 2,400 vehicles per hour is the daily rate. Capacity is 3,600, and during the incident is 1,800. You want to look for T1, T2, and T3 are your key spots. Incident occurs at T1. Incident clears at T2, Q dissipated Q3. Maximum queue length is the neon yellow line there going vertically. Maximum time in queue is the pink line going horizontally. Total delay is the entire area within the curve. That's when the queue dissipates. Because of a minor collision, one of two southbound lanes of Route 8 is blocked at 8:13 a.m. The normal freeway capacity of 3,600 vehicles is reduced to 1,340 vehicles per hour. The southbound flow rate on February 12th at the same time of day is 27:15. The blockage is removed 15 minutes later. Go ahead and draw it. Y-axis, cumulative vehicles. X-axis, time. Normal arrival is 45.25 vehicles per minute. Congestion is 22.3 vehicles per minute. The max rate is 60 vehicles per minute. T1 is 8:13. T2 is 8:28. Max queue length is T of time equals T2 minus T1, which is 15 minutes. The queue length equals 344.25 vehicles. That's the vertical distance at T2. And then find the time in queue equals T times 22.3 minus TI times 45.25. So T1 is 7.39 minutes. So T equals T2 minus TI, which equals 7.61 minutes. Max time in the queue. Normal T3 is when everything goes back to normal, equals T2 minus T1 congestion arrival plus T3 minus T2 arrival rate. Break that down. It's equal to 38.3 minutes, which is equal to 8:51 a.m. Traffic signal terms. Phase, each signalized movement or combination of movement. Ring structure, map of all phases. Interval, green, yellow, or red time. Split equals green plus yellow plus all red. Cycle, time to service all phase splits. Offset, reference time between intersection for progression. Calculations for cycle time. C equals the minimum necessary cycle length in seconds. L equals lost time for cycle in seconds. X equals the critical value of volume over capacity ratio for the intersection. X equals 1 at full capacity. N equals the number of critical lane groups. L equals the total cycle loss time, which is equal to startup delay, typically 2 seconds, plus yellow plus red. As you see there, the equation, so your cycle equals your loss time times your critical ratio divided by your critical ratio minus your critical lane groups V over S. The Webster cycle for optimum length equals the cycle optimal equals the optimum cycle length in seconds. L equals the loss time for the cycle in seconds. N equals the number of critical lane groups. L equals total cycle loss time, which equals the summation of startup delay, typically 2 seconds, plus yellow, plus all red, minus 2 seconds. You can see your equation there. C opt equals 1.5 L plus 5 divided by 1 minus the sum of your VS critical groups. Allocation of green time. G equals your effective green time for phase I. V over S critical equals your flow rate for your critical lane group I. C equals the cycle length in seconds, and XI equals VC ratio for lane group I. GI equals VS over CI critical group multiplied by C over XI. Example 10. You have saturation flows which would be provided for you for a 3-phase. So phase 1, eastbound left is 1750, westbound left is 1750. Phase 2, saturation, eastbound through and right, westbound through and right, 3,400 vehicles per hour. Phase 3, southbound left, 450, northbound left, 475, southbound through and right, 1,800, northbound through and right, 1,800. The actual flows, you can see there as well for phase 1, phase 2, and for phase 3. In the cases there, all the ones with the checks are the highest ratio in the problem. So those are the ones that you use for your VS here, your VS here, and your VS here. Only one VS per critical group. Minimum cycle length. L equals XC over XC minus the summation of VS. In this case here, you can assume X is 1, meaning at full capacity. That's equal to 43.8 seconds. At the top, when you're talking about lost time, equals 4 seconds per phase, which is approximately 12 seconds per cycle. Down at the bottom, the more conservative approach, XC is equal to 0.9. 12 times 0.9 divided by 0.9 minus 0.76 equals 62.1 seconds. That's a more conservative time. On the exam, they will give you XC. Optimal cycle time. Webster's optimal cycle length equals 1.5 times L plus 5 over 1 minus the summation of your critical groups equals 83.9. So your VS CI critical groups is what you see at the top here, which is the same as what you have here for your VS critical summation and your VS critical summation. Example 11. Let's use the numbers from the last example. Green times for your allocation. So your greens are going to be equal to your VS for your critical groups times L over XI. So for the first one there, it's 0.171 times 62 seconds, which is the cycle length you calculated in the last one, divided by a conservative X, which is 0.9. You can see that that's 11.8 seconds. For G2, it's 0.338 multiplied by 62 divided by 0.9, which equals 23.3 seconds. G3 is going to be equal to 14.94 seconds. When you sum all those and you add in the lost time for the cycle, you will equal your 62 seconds, which is what we suggested right here at the bottom for the more conservative approach. The same philosophy can be used for the Webster's as well. Clearance interval. Total clearance time equals your yellow multiply or plus your all red times. T is your perception reaction. V is your average vehicle speed on the approach in miles per hour. A is your deceleration rate. Could be anywhere between 10 and 11.2. W is the width of the intersection. L is the average vehicle length, 20 feet. I would suspect that they will provide most of this information for you. Yellow equals the equation above. As you can see there, we put in our values and we get approximately 4 seconds for our yellow time. Now, if you add grade, you can see the uphill, the 0.03 in the denominator shown at the bottom, and you can see how that changes to 3.7 seconds. So obviously, trying to slow down going uphill is your friend. The all red time equals your width plus your length over V. As you can see here, the width of your intersection is 24 feet. The length of your vehicle is 20 feet. Velocity there is 40 multiplied by 5280 divided by 3600, which is your feet per second conversion, which is equal to 0.75 seconds. So your total time equals your yellow plus your all red. And this one is for our level terrain calc, which is equal to 4.65 seconds. You should be able to do this problem in just a few minutes. I would suspect that they will give you W and L. This is a plug and chug. Pedestrian calculations. You need to make sure that the pedestrian doesn't violate any of your green allocations. The top one is for crosswalks or effective walkways less than or equal to 10 feet. The second equation there is for crosswalks or effective walkways greater than 10 feet. And you can see the common values there for your GP, which equals your minimum pedestrian green time. 3.2 seconds is your pedestrian startup. L is the length of your crosswalk. SP is your walking speed. NP is the number of pedestrians crossing during an interview. And WE is the effective walkway width. In this example here, you can see in the top, L is equal to 40 feet. Number of peds is 15 peds, both ways per phase. Effective walkway is 9 feet. You can see the startup there It's 18.7 seconds in that equation. The second one, we're going to increase the effective walkway to 13 feet. And you can see there, in that case there, it's 17.7 seconds. These greens are the minimums for crossing and need to check against the GP values that were calculated earlier. The GP values that we're talking about are these green times here. The next topic that we're going to discuss is multi-lane highway capacity. Estimating free flow speed. The FFS can be estimated indirectly when field data are not available. FFF equals your base free flow speeds minus your lane width, minus your lateral clearance, minus your median type, minus your adjustment for access points. A 6-lane undivided multi-lane highway has a base free flow speed of 65 miles per hour. There are approximately 10 access points per mile. Each lane is 11 feet wide with a lateral clearance of 2 feet. What is the multi-lane highway free flow speed? Based on this, in this example, 6 lanes, the ideal flow is 65 miles per hour, and you can see the lane widths there. You're going to need to look in your book to have the values provided for you. You will not be able to calculate your FLW, your FLC, your FM, or FA without the material in the book, or they'll have to provide it for you. But in this case here, it's 56.2 miles per hour. The second thing that you're going to have to do in multi-lane highway capacity is determining the flow rate. There's 2 main adjustments that are required for the highway flow rate: peak hour factor and highway vehicle factors for heavy-duty vehicles, trucks and RVs. So your flow rate is going to be equal to your VP equals your 15-minute passenger car equivalent flow rate in passenger cars per hour per lane. V equals your hourly volume, vehicles per hour. Peak hour factor equals your PHF. N equals your number of lanes. Fraction of heavy vehicle adjustment factor and driver population factor are what you're looking for in this equation. Always, you're going to have to calculate the FHV. FP is typically 1. FHV equals 1 over 1 plus PT multiplied by ET minus 1 plus PR, ER minus 1, where ET and ER, the passenger car equivalents for trucks, buses, and RVs. PT and ER are a proportion of trucks, buses, and RVs retrospectively in the traffic stream in decimal fraction. Fraction of your heavy vehicles is the adjustment factor for heavy vehicles. Other things that you may have to go into, although probably not, is flow rates beyond the break point. And these are the equations that you can see at 60 miles per hour based on vehicle speeds. So speeds beyond the break point at free flow speeds of 60 miles an hour, similar notation to other speeds, is 1,400 passenger cars per hour per lane. And then VP is the demand flow rate under equivalent base conditions. I would encourage you to go back to your notes from Intro to Transpo and see more about flow rates beyond the breakpoint. My guess is on the exam, if they ask you this style of question, they will not ask you for this, but you should be aware that this is something that potentially could be there. Example 15. The same 6-lane multi-lane highway has an ideal flow of 65 miles per hour. Each lane is 11 feet wide. A few sections have grades greater than 2.9%, but none of these sections are longer than a quarter mile. The directional weekday volume is 200 vehicles per hour, 2,500 vehicles per hour, sorry about that, and one direction is mostly commuter. The traffic stream consists of 8% trucks, 7% buses, and 4% RVs. The peak hour factor is 0.85. What is the passenger car equivalent flow rate? I would also encourage you to go back to your notes and look at how to calculate peak hour factor. Peak hour factors are never greater than 1, and it's very uncommon to see a peak hour factor below, say, 0.7. In this example, base free flow speeds, you can see the givens at top. The first thing that you will always see is that flow rate, so vehicle P equals your V over your peak hour factor times N times FH times FP. Almost always you'll have to calculate your fraction of heavy vehicles, and you're going to have to look for your ETs and your ERs and tables. And again, those were in your notes. I would flip through the NCEES book that you're allowed to see to make sure that your ETs and ERs are there. Go ahead and solve, and you'll see in this case here, your fraction of heavy vehicles is 0.92. Plug that back in, so your VP is going to be equal to 1065 passenger cars per hour per lane. Now, determining the level of service. Define and segment the highway. Estimate the free flow speed. Determine the average passenger car speed and level of service. And determine the density of the flow. Density equals your flow rate divided by your average passenger car travel speed. So what we did here is you had your speed that we calculated first. Then we calculated your flow, and you can calculate your density. And you can see it here. Your density equals 18.9. Again, you want to make sure, as this one says here, this example does not violate the breakpoint value because it's less than 1400. If it was greater than 1400, you'd have to use the other equations, but in this case, it's not. You would also need to be provided in the book what the level of service criteria would be. In this case, it's equal to B. They would probably just ask you what the density is. It's 18.9. Again, you can look at the examples in our book. Freeway highway capacity is done in a very similar way to the multi-lane capacity. Free flow speed equals base free flow speed minus FLW minus FLC multiplied by these values here. You can see here is base free flow speed is 75.4 miles unless otherwise given. And you can see the other variables in there for estimating free flow speed. Estimating the service rates is done exactly the same way that we saw for the multi-lane highways, where VP equals 15-minute passenger car equivalents and passenger cars per hour per lane. V is the directional design hourly volume. Peak hour factor equals PHF, again, typically between 0.7 and 1. And its number of lanes. Make sure that your N is corresponding to the V on your numerator. Fraction of heavy vehicles is your heavy vehicle adjustment factor, and FP is your driver population, and thus otherwise stated, it will be 1. Similar to before, fraction of heavy vehicles with a numerator of 1, and you can see down below the PT, the ET, the PR, and the ER. Make sure you split them out. ET is passenger car equivalency for trucks and buses, and ER is just for RVs. These are the breakpoints. So for a 75 mile an hour section, speed beyond the breakpoint of free flow speed of 75 miles per hour should be considered in these equations here. And you can see it at 1,000, 1,200, 1,400, and 1,600. It's the last numbers in those equations. Again, similar to the multi-lane, I would doubt that you will see this on the exam. Density, same as before, V over SP, where D is the density in passenger cars per mile per lane. VP equals flow rate, passenger cars per hour per lane. S equals the average passenger car speed in miles per hour. Example 16. The freeway conditions are as follows. 6-lane rural highway, 3 lanes in each direction. Directional design, hourly volume of 4,075 vehicles per hour. Lanes are 11 feet wide. Right side shoulder is 4 feet wide. Total ramp density is 0.25 per mile. Rolling terrain, 10% large trucks, buses. Peak hour factor, 0.9. Let's look at this again. The top one there, you're gonna see free flow speed equals 71.7 miles per hour. Those are just pull the values from the tables that will be provided for you. If you do not have those tables, they won't ask you this style. They will just give you the free flow speed. VP is your passenger cars per hour per lane, and you can see that that's related always again to the fraction of heavy vehicles, which is the 0.85. And you can see down there my VP equals 1775.6. So you want to check against the breakpoint. You use the closest one, which is 70. And so in this case here,
we're way above where we're supposed to do. So look at the stuff in parentheses, and you can see how the speed gets converted to 66.2 miles per hour. And you can see that the VP has a level of service of 26.8. Sorry, that's your density, not your VP, is 26.8. And that gives you a level of service of D. So in the multi-lane, you did not go higher than the break point. In the freeway, you did go above the break point. Not a big deal. You just go ahead and convert it. My suggestion is look in the book and make sure that the equations here are provided or any of the tables are provided for your use. The next step is planning. The basic things that you're going to look at are the 4 steps of the planning process. A planner assumes that a trip maker considers the following questions. Should I make the trip? That's trip generation. 2, what is my destination? Trip distribution. 3, what mode of transportation? Mode choice. 4, what route do I take? That's your trip assignment. Trip generation. Estimating the number of trip ends. Ends refers to the start and finish of a trip. A single trip always has 2 trip ends. Trip origin is production end. Trip destination is attraction end. Trip generation methods, ITE report, cross, classification, and regression models. My guess is if you see this on an exam, it will be a basic regression model where you solve for Y. Trip distribution. How many trips that begin at a given origin will end at a given destination? Trip generation, there's your TG. Figure out number of trip ends in each zone. TD. Figure out trip interchanges with the subscript T, I, J. The number of trips produced in zone I and attracted to zone J. Mode choice. Many mode choice model applications are used to figure out how to get people out of their SOV and into their HOV or transit. So, you would try to reduce congestion, improve air quality, reduce fuel consumption. Trip assignment. Each person wants to take the path with the shortest travel time. The shortest path time is easy to determine if you are the only vehicle on the road. However, travel time increases on optimal length as the road approaches capacity. Therefore, other routes that may be no longer and distance become more attractive. The next topic that we're going to talk about is hazardous locations and safety. For intersections, you use crashes per million vehicle entering an intersection. So the intersection rate equals number of accidents times 10 to the 6 divided by the ADT, number of years, 365 days a year. And that will get you crashes per million vehicles entering an intersection. The other one that you will see is highway segment, crashes per million vehicle miles. In this case here, you take the segment rate equals number of accidents times 10 to the 6 divided by the ADT times the number of years, 365 days a year, and multiply that by the length. On the exam, they may give you 2, 3, or 4 different ones and say, pick which one is the safest. The safest is the one with the lowest intersection rate or the lowest segment rate. At this point, we have now covered the geometric design, streets, highways, and intersections, traffic capacity and flow theory, traffic control devices, transportation planning, including modeling, safety, and trip generation. At this point, I wish you guys the absolute best of luck on the exam. Please do not hesitate to go back through your notes that were provided for you in Intro to Transpo. And on that note, I wish you good luck at studying.